Alright, so this is the second video in the external engineering run-throughs, and as you can see, today we're going to be just running through the 2021 external, the multiple choice, and the question response as well. Should be about an hour long. Let's do it. Alright, so question 1. Conventional automotive torsion bars are manufactured using steel with a carbon content of 0.3 to 0.5%. So this is another metals knowledge that you're going to have to know and memorize, these carbon percentages for all the different types of steel. So you're going to need to know, let's see, low, mild, medium, high tensile, and ultra high tensile steel. And they could ask you about cast iron a little bit. So let's say 6. But you mostly need to know the lowest 5. So the first range that we have is 0.07 to 0.15% carbon. And that's your low carbon steel. And because it's low, it's going to be a little bit of a plastic material compared to the other steels, and we're going to mostly use this for automobile parts, body parts, which I think their specific wording is automotive body parts, and wire products. Let me bring up. And the next section is going to be 0.15%. I've noticed that some sources will go and say like 0.07 to 0.15, and then they'll jump to 0.16% to 0.3% carbon. And I'm not sure why they do that. I'm very confident that it's 0.15 is the boundary, and if there's 15.5% carbon, it's not going to be low or mild. It's not something in between. That'll just be mild carbon steel. I don't know why some sources go and say 16, because it's a float, not an integer. So in your mild carbon steel, this is it's a really common material. You can be using it for structural sections and plates. You can also use it for boiler plates, stamps, and it's another thing, forgings. So there's two metals actually that are used for forgings, and that's mild carbon steel and also medium carbon steel, which is the next one along after these. Whoa, what the hell? What? Okay. Alright. So the next section is going to be medium carbon steel, the third type of steel that we're going to look at, and that is from 0.3% to 0.6% carbon. And so yeah, we're going to use this for forgings again. Whoa. What else are we going to use this for? Automotive component parts. So this is big emphasis on the components here. So we're talking about gears, shafts, axles. Those are all going to be medium carbon steel. But the body parts, stuff that we want to absorb energy because it's tough. Well, not so much tough, but it's the ductility of the material ends up meaning that it just can absorb a lot of energy without having high stiffness and high jerking motion when you're running into something. So that's why we use low carbon steel for automotive body parts. But then the medium carbon steel has a great deal of thickness. So medium carbon steel is going to be your standard stress V strain. You're going to have that decent amount of stiffness there, decent amount of elastic region, and that makes it okay, never mind. Continue. The next thing we're going to look at is high carbon steel, and that is 0.6 to 1.25% carbon. And so this is going to be primarily used for things that we want to be hard and stiff, but also they need to be durable, and we don't want it to be so hard that it just fractures. And so then we're going to be using that for like industrial knives, tools, punches, high strength spring materials, and wires. So yeah, And there's a little distinguishing difference between high carbon steel and ultra high carbon steel. And that's the fact that, well, first of all, high carbon steel is going to be 1.25 to 2% carbon. But also, we're going to just make a little adjustment to the materials, the applications that it's used for. That's going to be that we're going to use ultra high carbon steel for non-industrial and or highly tempered, just tempered knives, tools, etc. And that's knives, punches. Oof, what is this there? I feel like there's another one that I'm missing. Yeah, so cutting tools, large machine parts, that sort of stuff. But QCAA wants you to know that it is non-industrial that we use it for. And the only other material that they could ask you about is cast iron. Cast iron is roughly 2% to about 4.15, roughly, I think, percent carbon. They won't ask you on this, but it is just good to know sometimes. And cast iron is cast iron. It's a really hard material. It's not malleable at all. You can't really shape it into anything. It's cast iron because you have to pour the iron into a mold if you want to make anything that's shaped. It's almost impossible to hammer it into anything, even when it's like hot. So that's why it's called cast iron. And the question itself, that's just asking automotive components. Oop. So that's going to be medium carbon steel, which is D. Logic gates question, logic circuit question, sorry. When the output from the logic circuit is 1, the input to the circuit is... So instead of reversing this, I'm going to just take a look and do a process of elimination. So if P and Q are both on, we're going to get a 1 there. If R is on, that's off. This is going to be on. That's going to be on. That's an OR gate, so this is going to be on. And if S is on, that's going to be on, but that's an XOR gate. So it's one or the other, but not both. So that's going to form 0, which means it's not A. And let's go erase all that. Let's put a 1 there again. If P is off and Q is on, then we're going to get a 0. R is on, then we're going to get a 1 here. That's going to be a 1 there. That's off. And R is going to be off, so this is going to be on. Oh, sorry, R is on. Oh, sorry, we're looking at B for this one. R is on, so it's off here. Both off, so that's off. Which means S would have to be on, which it is. So it's B. Can't be D, can't be C. Alright. Question 3. Stress for strain graph. Stiffness of a material. That's J. Because the stiffness of the material is essentially the length of the proportional area. It's the proportional limit up there. You've got the yield there, ultimate tensile, fracture point. But remember that the point between the UTS and yield is strain hardening. And the area after that, before it fractures, is the necking zone. And that's the plastic region. This is... Oops, sorry. That's elastic. My bad. And that's the plastic region. Area under the curve is toughness. And the amount of strain you can undergo without fracturing is the ductility. So, answer is A. Inclined plane. Just write down a formula first. This looks like there's no external force, so we can probably just do this. Box slides down the slope as shown if the coefficient of friction between the box and the slope is 0.2. What is the acceleration of the box? Alright, so if we're talking about acceleration, then we can just divide all this by mass and go... simplify a little bit. That's going to be 9.8 sine 25 degrees minus 0.2 cos of 25 degrees. Chuck that in the calculator. And that's going to be 2.36 meters per second squared. That's going to give us C. That's the right answer. Question 5. Alright, crane question. It's a load. Distance of 20 meters. Pulley system. Alright. So it's implied that there are 2 pulleys here, and there are 4 active wires to pull up the load. That main winch cable is the effort wire, and it's not counted as an active wire. That means that the mechanical advantage of this system is going to be equal to the number of wires, active wires, which is 4. And if this load is moving 20 meters, that means this system up here also has to be moving 20 meters. And if there are 4 active ropes, that means that we're going to have 4 times the length of material coming out at this end. So it's just going to be very simple. 4 times 20 is going to give us 80 meters, which is answer B. Question 6. Crowbar question. Alright. So, FE, effort, force of the effort, 55 newtons, applied to the crowbar at position P, which generates a force of 500. Force of the load, 550 newtons. It raises the floorboard by 20 millimeters, and that's distance of the load. If the distance of the effort, Q, is 700 millimeters, what is the efficiency? Alright, so we pull out our formula. Efficiency is MA on VR. This is on the formula sheet. And let's do a little, it follows that. MA is force of the load, divided by force of the effort. And that's going to be 550 divided by 55, which gives us 10. And our velocity ratio is distance of the effort divided by distance of the load. And that is 700 divided by 20, which is 35. If we do our efficiency formula, we're going to have 10 on 35, which is 28.57% efficient. It's pretty bad. Which rounds to 29%. And that's answer C. Okay. Question 7, another efficiency question. Efficiency is 0.75. Distance of the load is 3 meters. And force of the load is going to be 120 times 9.8. And that's 1176. And it also gives us the distance of the effort, which is 8 meters. And we're looking for force of the effort. So let's do some substitution into, actually let's not do a substitution yet. Bring out this formula again, rearrange for MA. Rearrange for force of the effort. It's going to be DLFL over efficiency DE. And what's that? 3 times 1176 over 0.75 times 8. And that gives us 588 newtons. That's answer D. Question 8. So this one has some solubility regions. So this area here, that's going to be tin dissolved in lead, because we've got mostly lead over this side, and that means that, you know, lead is going to be the solvent and tin is going to be the solute, and we're going to have the opposite over this side, so that's just going to be lead in tin. And that's tin and lead in the form of liquid. So, sorry. And this is going to be tin plus liquid. And this is just liquid, and that's just alpha. Okay. In the thermal equilibrium phase diagram, a liquidus line is represented by the letter H, because this curve separates the liquid from the two-phase regions, the solids and the liquids. That's the liquidus line. And the one that separates it from the solid soluble states, that's the solidus. And these other two lines, I've actually just forgotten what they're called. It's sol something. Solvus. That's the solvus line. So liquidus line, that's represented by H. Question 9. So work is force times distance, and the force we're experiencing is 1500 kilograms times 9.8, times by, convert this to meters, remember, 1.8 meters. That is 26,460 joules. And that's answer C. Exactly. Hey, a microstructure question. Very simple one. Whoa. So, hypereutectoid. Let's draw out the carbon phase diagram. Just very simply. This area here, this is austenite. It's denoted by the symbol gamma. There are some regions up here as well, but we're not going to worry about them. That's temperature. This is carbon composition. And this is very rough. Going to have another line like that, and then that is roughly it. So, let me think. This area here is austenite and cementite. That means cementite. Some liquid up there. This here, this is the peritectic point. They haven't asked a question on that before. I don't think they will. You know, it's good to know though. That's the eutectoid point right there, and that's the eutectic point. We're mostly interested in the eutectoid and eutectic points. Can't erase that bit. This area is going to be ferrite, so ferrite and cementite. Let's move that out of the way. Because the eutectic composition, that's going to happen... sorry, not eutectic. Eutectic, we're focusing on eutectoid. So the eutectoid composition, this point here, happens at exactly 0.8% carbon. And it's important because that's where we're going to see the intimate formation of ferrite and cementite, or perlite phases. And before this line, so this region over here, that is the hypoeutectoid formation. You're going to see hypoeutectoid, which is more similar to a ferrite microstructure, but you will see just small regions of perlite, but also a really thick grain boundary of ferrite as well. But at the 0.8%, that is a eutectoid composition, or formation. And that's going to be your standard perlite. So, you know, you're going to have your little cells, and you're going to have the lamellar lines. All of them will have lamellar lines. But this region past here, that is going to be the hypereutectoid formation. I can't spell. What that means is we've got too much cementite. This means we've got not enough cementite. We've got just the right amount to make perfect perlite. And this means we've got too much cementite. So now we're going to start seeing just like... We're going to see perlite. But we're also going to see these really wide grain boundaries. It's like they're being stretched. And those grain boundaries are going to be filled in with excess overcarbonated cementite. It's no longer able to form those lamellar regions because there's just not enough ferrite. Let's fill that in a bit more. And so what that's going to mean is that this in the grain boundary, what the question's asking, if you look at the arrow, it's pointing at the grain boundary. The answer to that is going to be cementite, which is A. Because again, there's just too much cement. It's hypereutectoid, which means there's too much cementite, and that means it's going to get left over in the grain boundaries. Okay, so multiple choice done. Let's head on to the question response. So this one looks like it's a little bit shorter, but there's a few more marks than 2020, if I remember right. Could be wrong. But yeah, let's give it a shot. Question 11. Sketch a stress strain curve for nylon. So nylon, that is a... Oof. It's a really tough material with good thermal and chemical resistance. So... makes it really good for anything that's going to be abrasive. So wear pads, if you've ever put elbow pads on, plastic elbow pads, if you skateboard or something, those are probably going to be made out of nylon, because when it's wearing down, you get a lot of heat and a lot of friction, and nylon's really good at absorbing that thermal energy. Forget the other one. So what we're going to see for nylon is it's going to be very tough. It's going to have a big area under the curve, but it's also not going to have a yield strength because it's plastic. They generally don't really have the yield strength. Does it ask us to label it? Alright, so say the proportional limit of my bad drawing is about there. They usually want us to also label Young's modulus, so let's do that. And then obviously the fracture point. That was horrible. Fracture point. And the ultimate tensile strength. Okay, so we're not really... The marking guide for this one is... They want you to know a bit more than it really says on the syllabus. You're not supposed to know this about nylon. Then again, I probably shouldn't have given it so much strain. So what the answer wanted me to do was put the proportional limit before the 20% strain, and have the rupture point before 80%, which is good. I did that. They also want me to identify toughness, which for some reason they've actually put on the marking guide. If you pull it up, you'll see that they've put an arrow down here and labeled that as toughness, which is wrong. Toughness is the area under the curve. This point here, that's ductility. So they've actually just referenced ductility and said it's toughness. That's wrong. This point here is ductility, and the area under the curve is toughness. They also give you a mark for Young's modulus, and that is it for the 4-mark question. Question 12. 4 fields of knowledge used by a biomedical engineer to perform their role. So biomedical engineers, they have a range of duties that they can be doing. They can be operating software, like a diagnostic software, or machines as well. Anything with the medical software and machines, they'll be operating those. They'll also be potentially making that software and machines. Or they could be making prosthetics and internal human devices like a heart pacer, etc. What do you call that? Medical devices. So, because they're working with software and machines, they're going to need to know mechatronics. They're also going to need electronics and software. So make sure you don't get electronics and electrical mixed up, because electronics it's the control of the flow of electrons. So that's going to be like logic gates. Electrical is a conversion of electrical energy to other forms of energy. So that's like... So electrical is more just diodes and switches, so your cells, and what else could we put in here? Resistors. Maybe even a variable resistor. So that's electrical. But electronics is when you're going to be working with logic gates themselves and more complex things like Arduinos, etc. I can't think of a fourth one, although I'm not giving this much time. Of course, alright. So what they've put is... Alright. They've also put electrical in here, but I'm not sure they would need to be working with electrical... I don't think they would need to be working with electrical knowledge. They could just use electronics and probably be fine. They haven't put mechatronics. But their answer scheme, this is just a sample response. The marking criteria... Hang on. So they've put electronics, electrical, mechanical, and materials is the other one I should have put down. But the answer scheme, marking scheme, is just providing correct knowledge types. But I'm going to debate that they don't really interact with electrical things that much, because I don't think when you're making a prosthetic or medical device, you're probably going to be looking at sensors and having logic gates for those sensors, you know, and getting an output for that. So, yeah, I'm going to disagree with electrical. They did say mechanical as well, but, you know, mechatronics is essentially both electronics and software and mechanical, so that could just count as 3 ticks, and they could remove that one. But I would be safe and split this one up into its subsections if you're running out of space. So, yeah. Alright, question 13. This is our carbon phase diagram. So they have asked a question about cast iron. 3% cast iron. So, if I remember correctly, 3%'s about here. No, that can't be right. Yeah, this is about 4% carbon, I'm pretty sure. And then you've got 0.8% here. That's like 2.14%, so 3% is going to be here. Because if you remember, cast iron, so they have asked a question about this. Cast iron goes from about 2% carbon to about 4% carbon, and it's the region between this point here, which I don't think there's a name for, and the eutectic point, which is over here. So, what else? Explain how the microstructure of a 3% carbon cast iron changes during cooling between the eutectic temperatures. So this is the eutectic temperature here. It's roughly 1147 degrees Celsius. And the eutectoid temperature is about 727 degrees Celsius. So even though it says between the eutectic and eutectoid temperatures, I am going to start in the liquid and end in this completely solid area. So let's say we start off with both phases combining in a liquid, and then when they reach the eutectic temperature of 1147 degrees, we're going to see that this region, it's here, is austenite and cementite. So we're going to see that it's going to start forming semi-solid structures of austenite and cementite, but they're still going to be able to move a little bit. We could draw a little diagram off to the side. They're not really move, but they still still malleable. Very malleable. Okay, that was just wrong. They're not very malleable. And what's going to happen is as it transitions through the eutectic temperature down to the eutectoid temperature, we're going to see a decrease in the amount of austenite and the increase of carbon. And what we're going to see with that is, eventually, as it reaches the eutectoid temperature, we're going to see that there's no more austenite left, and it's all become, well, it's lost its carbon, and it's all become ferrite, which is alpha. And the process of that is going to form, well, for cast iron, it's going to form a hypereutectoid formation, and that's where we're going to have the large grain boundaries filled with excess carbon and austenite and cementite. Sorry. So we're going to have the ferrite forming the lamellar lines with the cementite, and then all the carbon from the austenite is going to join with the pure. It's going to join with the ferrite to make more cementite. Which is be a good idea to read the marking scheme for that. So the marking scheme is. Well, let's read the sample response for this explanation question. They've said that when the eutectic temperature of approximately 1147 degrees Celsius is reached, the residual liquid forms the eutectic mixture of austenite and cementite, along with the previously formed austenite dendrites. As the temperature drops towards point B, carbon precipitates out of the austenite to be deposited as growing areas of eutectic cementite. When the eutectoid temperature of approximately 723 degrees Celsius... Oh, so I got that wrong. It's 723. The remaining austenite with 0.8% carbon changes to perlite. So they could have added in there that the remaining austenite turns into ferrite, and which forms perlite, but that's being nitpicky. The marks there are for identifying that the liquid forms a mixture of austenite and cementite, and the carbon precipitates out of the austenite to form eutectic cementite, and that perlite forms at the eutectoid temperature. And then you also get a mark for the approximate location of the carbon, so that's just going to be... They'll probably pretty much give you a mark if you put it anywhere between this point and this point. They also wanted me to identify the points here as A and B, although they didn't ask me that, but I can see somewhat how they could expect that in the explanation. Question 14, explain how a tensile test for low carbon steel material can be used to determine the ductility of the material. So when we have a tensile test, what we're actually doing is we've got a machine, we've got these machines, and they grab onto the rod that we're testing. So this is the rod, metal rod. And as that machine moves upwards, it has sensors determining that tell it how far it's moving and how much resistance it's seeing, and that metal rod is going to start necking. So this is what necking looks like. And we're starting to see it really stretch, and eventually it's going to fracture completely, and we're going to be left with two halves of the material. And for low carbon steel, that is not going to encounter too much resistance at all, but it's going to elongate quite a bit. So we're going to see a very short stiffness region, and then we're going to have a yield. And it's not going to be very high. We're going to have a lot of necking. And let's label our graph there. Fracture. Yield. Could also label proportional limit. Let's just say PL and Young's modulus, because I don't have enough space. This area here is strain hardening. Alright, so the points there. So the answer for this is the stress strain graph generated as a result of the tensile test displays the material's ability to withstand continued strain after yield, which is indicative of the material's ductility. This occurs within the area of the graph that shows plastic deformation of the material up to fracture. Now, I believe the ductility itself is just the amount of strain that it can undergo before fracturing, and I don't believe it's just within the plastic region. And the points there that you get is for withstanding strain after yield point, or ultimate tensile. Why? That is not what the question is asking. So the question is asking, how can the tensile test for a low carbon steel material be used to determine the ductility? So again, we're seeing that QCAA is giving marks out for something that they're not actually asking for in the question. So the other two marks for that first part is plastic deformation and fracture, which yes, you should be mentioning that. And providing an appropriately annotated stress strain diagram that shows the plastic region. That's my bad, I should have put that in. I didn't think that was particularly necessary for determining the ductility of the material, but you know, the upper yield point and the point of fracture. Now these logic gate, drawing these logic circuits, these are maybe one of the worst worded questions, because this last part here is ambiguous. Let's read it. An automated machine fabricates a metal component using a punching tool. This machine includes sensors that allow it to operate only when the punching tool is detected as correctly inserted within the safety guard and the punching position. When either a component is detected as correctly positioned, with the manual shutdown switch not activated, I see. And when either a component is detected, or the manual shutdown switch not activated. All sensors send a 1 input for a yes activated condition and a 0 input for no not activated condition. So that would mean that the safety guard, if the safety guard is on, does that mean it's in the punching position? No, okay, so if it's positioned in the punching position, it's going to be off. Manual shutdown switch, it's on if it's activated. Component detection, so that's fairly simple. Punching tool detection activated, alright. So this, I don't think this was the one that I was remembering. There is a much worsely worded one of these that we will come across probably the next video. So, let's label all of these. And draw some lines out. Machine includes sensors that allow it. So the punching tool has to be on. And the safety guard has to be off. So let's swap these around. So this gate here is going to activate when P is on, punching tool is on, and the safety guard is in the off position. And that's going to be our first part. Put a NOT gate here so that the manual shutdown switch is not activated. And then we're going to have an OR gate. And these two have an AND connecting them. So again, this is not what QCAA has written, so let's see what they've done. They didn't put a NOT here, which leads me to believe that they think the safety guard is on when it's in the punching position, which doesn't really make sense, because it should be operating only when, what they're saying is, it should operate only when the punching tool is detected and the safety guard is on. Which doesn't make sense, because if the safety guard is on, shouldn't you be not able to operate it? So I'm going to stick with my logic gate here and say that this is the correct way to do it, for this part. Because they just don't have this part here. And the other thing that they've done is, instead of putting an OR gate here, they've put an AND gate. Which, if we look back up here again, we're going to see that the second half of the conditions, just between these areas, and that's that gate there, that AND up there, when either, specifically, either a component is detected, or the manual shutdown switch not activated. That is an OR gate. There's no question about that. It's either. And then the marks in that question go to appropriately annotating it. I don't understand what that really means. Okay, so they want me to put 1s and 0s. I just assumed that was common. So they want me to put 1, 1, and 0? No. Because they've done that one. They've put 1 and 1 for that one. But because they did it wrong, I should be putting it 0. And they want me to put a 1 here, and a 1 there, and a 1 there. I don't see why you have to do that. These should be assumed. That's the whole point of a logic circuit, is that if this is on, that means it's active, which means this line is active, which means this line is a 1. And if it's off, then it's not active. That's why we put a variable here. The other thing you could do is draw a logic table for this. And they also... What? Correct sensor labels, oh yeah. And 4 marks is just for the correct gate itself, but they don't. This time they haven't given any marks for the logic table, but I would recommend doing that. I think I've seen that before. Okay, question 16. Machines used. Alright, so the diameter of this rolling pipe here is 0.25 meters. And what we're going to do here is we're going to see, first of all, how much I have to move A, this turning circle here, to do 1 revolution of B. Oh, it's already told us it's a meter. So, distance of the effort is going to be 1 meter. Pi times 0.725 is going to give us the amount of rope that drops from 1 revolution of turning A. And that's going to be roughly 0.7854 meters. And if we want to move it 10 meters, then the number of revolutions that we're going to have to do is 10 divided by 0.7854, which... Oop, that is 12.73 revolutions. And that's 12.73 meters at the distance of effort, because the turning circle is 1 meter. And then the distance that the load travels is 10 meters. So... do we assume that this is 100% efficient? It looks like we might have to. Yeah, okay, so they've just assumed for this question, because that efficiency is 100%, so MA equals VR. For some reason, in the sample of the response I said efficiency is 0, but then stated this. Another wording inconsistency. And that's going to be distance of the effort divided by distance of the load, which is 12.73 divided by 10. Let's do more accurate, 1.27. The question itself is asking for work and mechanical advantage. So if the bucket's 10 kilograms, that's going to be 98 newtons. I'm going to divide that by 1.27. because that is the mechanical advantage. Means the force that we're lifting is 77.17 newtons. So work is just going to be that times the distance, which is 10, so 771.7 joules. So they've done a little bit of a... So they've tried to trip you up here. I may have fell for it. And so while the work done, while the mechanical advantage can increase, the work itself doesn't. It's still the same force that is being transported the same amount of distance. Mechanical advantage only affects the force that you apply at the effort. It does not affect work. So this first half of the question is irrelevant from the second, which is where we're going to go work equals force times distance, and then we are not going to actually fill in that formula, make it a bit easier on ourselves, and substitute it over here. That's going to be mass times acceleration, 980, 10 kilogram bucket times 9.8 times the distance of 10 divided by 30. 98. Oops. And that is going to give us 32.7 watts. And the marks there is formula for work, formula for power, correct value of MA, and determination of work done and power used. I completely forgot that I had to actually figure out the work. Although I did actually, in the end. I could have just written 980 divided by 30 and they would have accepted that. Another one of these questions that I absolutely hate. Talking about sustainability issues now. Alright, so I give up. I've already done my external. I was very happy with it. I don't want to do these questions anymore. let's unpack what QCAA has written. So they've said stoves in developing countries such as India use biomass, such as timber, as fuel. Burning timber has been detrimental to the environment by contributing to poor air quality, so they've listed a disadvantage. So this is the problem. And the solution is the use of high-tech alloys and ceramics to develop low-cost stove solution. They've improved the burning efficiency, so it's low cost and improved efficiency. Ooh. Efficiency by 50%. And reduced smoke output by 95%. This reduces the mass of timber that is burned and has long-term and short-term community benefits, including, here are the 2 benefits that they're going to list: improved air quality and reducing the effect of burning timber on global warming, which I'd argue is the same thing. Improved people's respiratory health. It's so hard to write with this. At least it's not a mouse. And the points there go to identifying the problem and explain how they've used a relevant solution, which I forgot to list down, and used relevant knowledge. Explains the reduced environmental impact, relevant community health benefit, and another relevant community health benefit. So, I still don't like these questions. This one was easier than 2020's. My brain isn't working though at the moment, so I'm not going to. So I didn't attempt it. That's about it for that. For these questions, it is good to go and take a look, try to remember some. I think when I had my external just recently, they had another one of these questions, and they wanted to know technologies used for floods, and I said drones, because these are not dependent on roads and other flooded infrastructure and can help in spotting people that need saving. And they can even deliver supplies to those people if they're too far away. Alright, section 3. So this is B and that's A. And they want to know the percentage of solid and liquid material present for an alloy of 20% metal A. So that is there. At 900 degrees. Okay. That is our composition liquid point, and that is our composition alpha point. And that's composition of the origin. So, this is 5 mark equilibrium diagram, so we're going to need to note a couple things here. The composition of the alpha, so this is going to be the composition of the solid formation at that temperature. And it's going to be 100% metal B, while the composition of the remaining liquid is going to be, let's say, 50% A and 50% B. And the solid and liquid, we're just going to be doing lever rule. So I always like to start with liquid because I remember the formula. And that is going to be 0, 0 minus CO, which is 20, over CL, which is 50. And that is 40%. I could have done that in my head. Why did I put that in a calculator? And so, therefore, weight of the solid is going to be 60%. Weight percent. Now, we don't say A or B here because it's not the weight of the solid, you could say it's going to be... Sorry, no. You might think to put B or A here, but you shouldn't do that because it's not. This is just how much of the... This is not determining how much is B and A. That is what the composition alpha and composition liquid points are for. This is just determining how much is liquid and how much is solid. This is quite a difficult question. They did not give much room. If I remember right, this... Oh no, it was a different one. Is it here? No, it's not here. Must be in the next exam. Let's start labeling. 5 meters per second. So, mu is 0.4. So, we want friction force to equal the final force. Not final force, just arbitrary force pointing this direction. Friction is going to be mu mg, and the mass is going to be the combined mass of these two. And the force exerted by the package will just be equal to this. So, force is going to be 0.4 times 2.25 times 9.8. Which is 8.82 newtons. So they said that as the 2 kilogram package moves into the carton, and the force exerted by it is the mass that they use is just the mass of the carton, which in my mind doesn't make sense, because you should be using the combined mass of these two, because the friction is mu Fn, and if you're putting the package in here, then the normal force, it's going to be, the mass of the system is going to increase, meaning it's pressing harder on the surface, which means the normal force gets bigger, and the friction force gets bigger. So correct me if I'm wrong, but it shouldn't, mass should be 2.25 kilograms, not 0.25. Maybe I just don't understand what... No, I'm pretty sure I do. Other marks there go for free body diagram. And the working and the correct answer. So now they're doing mu k 0.3. Draw the free body diagram. Maybe we start with suvet. No, we need acceleration for that, so we can't do that. Ah, I was looking at the wrong diagram. This one. Can't start with... That force is wrong. So... So if the package is going 5 meters per second and the carton is going 2 meters per second, then we can effectively view this as stationary and 5 minus 2, 3 meters per second. And to conserve the velocity, the whole system is now going to be moving at 3 meters per second. And what we're going to do next is we're going to do the friction force. So the friction force is going to be mu k Fn, which is 0.3 times mass times gravity. And the mass is going to be the combined mass of the system, so 2.25 times gravity times 0.3, and that friction force is 6.62 newtons. We convert that to acceleration because we're going to use it in our SUVAT equation. So divided by mass. So actually, I didn't need to put that in. But you know, oh well. Acceleration is 2.94 meters per second squared. And now we can chuck in our SUVAT equation. Minus half g squared because we're decelerating. Our initial velocity is going to be 3. Wait, do we determine the distance? Yep. Oh, no, can't do this just yet. We need to know time. So let's do this. And t is going to be v minus u on a. And that is, the final velocity we want is 0 minus the initial velocity 3 over negative 2.94. It's 1.02 seconds. And now that we have that, we can do our SUVAT. Which is 3 times 1.02 minus a half, 2.94 times 1.02 squared. And that is 1.53 meters. And they did ask for it to be converted to millimeters for some reason, so let's do that. Don't forget to look out for that in questions. The marks there, it's just formulas and working, and the free body diagram. Alright, question 20. 3 more questions to go. So, that is 500 kilograms, and that's 200 kilograms. Through freely for 4 meters, and then we're going to have kinetic energy of 19.6 kilojoules. The moment of impact, energy is lost as heat and sound. So 5.4 kilojoules of energy. Determine the velocity of the piledriver just after impact. Alright. So first of all, let's take 5.4 off this. That's going to be 14.2 kilojoules. It's going to be equal to half mv squared. So 2840. Oh, not quite. But yeah. Oh my god. 400 times mv squared. V is going to be root 2400 divided by mass of the piledriver, which is 500. I'm going to take the root of that, and that is 7.54 meters per second. So I will check. And why is that wrong? Oh, okay, so now they respect that. Now they respect the system, the combination of these two different masses. And I forgot it. That's amazing. I did not have to rub all of that out. So let's do that again. 14200 is equal to half mv squared. So v is going to be root 28400 divided by the mass of both of them, 700, which means the entire system is, and individually they're both moving at 6.37 meters per second. Alright. If the pile and piledriver decelerate at a constant rate of negative 30 meters per second squared after impact. Alright, just do that. Wait, we need to first of all do v equals u plus at. Time is going to be v minus u on a, and that is minus 6.37 over the acceleration of negative 30, which is 0.212 seconds. Let's move over to this side and check into that. And that is initial velocity 6.37 times 0.212 plus a half of 6.37 times 0.212 squared. And that is going to be and I messed up. Give me a second. .49 meters. That is not what they got. What did you do? What is that formula? Oh, I forgot a minus. Whoops. That'll do it. Ah! Oh, okay. That is not an acceleration. That's a velocity. The acceleration is 30. Far out. Alright, third time's charm. Alright, there we go, that's the right answer. 0.676 meters, or 676 millimeters. And yeah, it's just working for those answers, for those marks. Alright, what's this? Okay, so velocity is going to be equal to u plus at. We know those. It's 0 plus 0.75 times 4, which is going to give us 3. From rest, the bucket is lowered with the constant acceleration. Determine the bucket's acceleration if the bucket has been lowered 25 meters after 10 seconds. So, we have this. Let's rearrange for t. Substitute, why did I rearrange for t? I'm looking for a. Whoops. A is 2s on t squared. And that is 50 over 100. That's half. Answer to one decimal place, yep. Okay. 2 more questions. Alright, 15 teeth here, and 100 tooth here, 100 teeth here. Cable drum. That's the diameter here, that's 500 millimeters. I'm going to convert that to 0.5 meters, and this is 20 kilograms, so 18.9 newtons. 189 newtons. And we're moving at a distance of 2 meters. Alright, power is going to be work divided by time, so force times distance over time. And that is, remember we don't include force, mechanical advantage, sorry, doesn't affect power and work done. So we're not going to do that. We're just going to plug it straight in here. 189 times 2 over 30. God damn it. Alright, so I can't read the question. So it says 2 hay bales here. I did 1 hay bale. So it's going to be 189. It might not even be right. 9.8 times 20. It's 196. That's why there wasn't even. Yeah, 196 newtons. So we're going to have 196 times 2 times 2. 2 hay bales, 2 meters, over 30. And that gives us 26.13 watts. Motor revolutions. Alright. So the first thing that we're going to need to do is figure out the circumference of this wheel drum, because the circumference is going to dictate how much one revolution of B moves the hay bales. So circumference is just going to be pi times diameter, which is 1.571. And if we do 2 divided by 1.571, we're going to get 1.27 revolutions are required. And so that's going to be, because B has 100 teeth, that's going to be 127 teeth. To figure out the amount of revolutions of A we're going to need, we just divide that by A's number of teeth. It's going to give us 8.46, or it wants us to round, just one decimal place, 8.5 revolutions. That's the correct answer, and the marks there are just working. Formulas and working. Last question, I think. Yep. Yeah, this is the other conveyor one. So assembly point, initial assembly point 1. This is going to be 2, and this is 10 meters. Acceleration equals 2 meters per second squared. Okay, so we need to figure out the time it takes for this initial setting. And got an acceleration. We don't know our final velocity, so we're first going to need to have... Ooh. We don't know T either. Let's have a look at a formula sheet for another formula. So, V equals root U squared plus 2AS. And that's going to be, initial velocity is 0, so 2 times 2 times 10. .32 meters per second. It's final velocity. We're gonna go and put that into this formula here. I'm going to rearrange for T. Oh, we didn't even need to know. Alright, my bad. 3.16 seconds. So if we're reducing the transfer time by 20%, I'm just going to times that by 80%, 3.16 times 80, 0.8, sorry. It's going to give us it's going to give us 2.53 seconds. So, let's find the acceleration that we need for that then. Acceleration is going to be 2s on t squared, or 20 over 2.53 squared. .12 meters per second squared. Let me try to write straight. So now that we've got that acceleration, 3.12, we're going to do, first convert it to force. It's the mass. It's 2 kilograms. 6.24. And we need to find the friction force, which is going to be our mu times the force of the normal, or mg. Alright, so then mu, do some rearranging, is going to be the friction force, or could sub in again, but it's not going to help, divided by mg. So for the second part of this question, while we are reducing the time by 20%, we are doing that by increasing the speed of the conveyor belt, but we also need to keep the component from slipping, increase the coefficient of static friction, which means that Ff is going to equal the acceleration that we calculate for the component, or just mass times A. So, if we bring that back down here, we can say that force of friction is going to be equal to 6.24 newtons, and we have 6.24 divided by 2 times 9.8, which is 0.318, or 0.32. That's all there is. So yeah, that question really just depended on understanding that the component needs to not slip, and therefore Ff and the acceleration due to the conveyor belt must be equal. So then you can just sub them in. Alright.